Hello and welcome to Mrs. Z's Chemistry. Today we are going to learn about redox reactions. Single replacement reactions are redox reactions, which means that is an oxidation and reduction reaction. In redox reactions, electrons are transferred between one substance and another. One of the species or atom or ion then will be oxidized and the other one is reduced. When the species that loses an electron and transfers it to the other one, that is the one that is oxidized. And the one that gains the electron or multiple electrons is the one that is reduced. To help us remember that, we have two different mnemonics. Oil rig is the first one. OIL is oil, and that is oxidation is loss of electrons. Rig, RIG, is reduction is gain of electrons. The other mnemonic, which is kind of fun, is Leo the lion goes grr. So we have Leo and grr. L is for loss, E is for electrons, O is for oxidations. So loss of electrons is oxidation and gain of electrons is reduction. You cannot have one atom or ion losing electrons without another one in the reaction gaining those electrons. An atom or an ion doesn't just lose electrons, and those electrons can't just go off into outer space or into nowhere. They are specifically being transferred to another species. So in redox reactions, you will always have one species being oxidized, losing the electrons, and one of the other elements, atoms or ions, is going to gain those electrons and be reduced. So in order to determine whether an atom has gained or lost electrons, we need to look at something called oxidation states. These can sometimes be confusing because they seem very similar to charges. They're often the same number as a charge, but we can find oxidation states even for molecules that are covalent and don't have charges in them. So here are the rules for the oxidation states. Group 1 metals, that's the very first column. Hydrogen, not included, but starting with lithium and then all the way down that column. They are always +1 in an ionic compound. The group 2 metals, the second column, are always +2 in an ionic compound. That's their oxidation state. And those two numbers also happen to match their charges, so those are easy to remember. Fluorine, all the way on the other side of the periodic table, is always -1, and that does in fact match its charge as well. But the other halogens aren't always -1. They can sometimes be different oxidation states. Oxygen is almost always -2. The only time that oxygen is not -2 is in this exception. Peroxide is a polyatomic ion that is O2 with a -2 charge, and therefore each oxygen has an oxidation state of -1 in a peroxide. The common ones are sodium peroxide and hydrogen peroxide. Most of the examples you'll see in the practice problems are going to not include the exception, and oxygen is -2, which matches its charge and makes it easy to remember. Hydrogen is almost always +1. This is the charge, or this is the oxidation state that matches its charge, but hydrogen can be -1 in a metal hydride. That just means a compound with a metal and hydrogen. So for example, sodium hydride. Sodium is a group 1 metal, so it always is +1. And then in this situation, hydrogen would be -1. Or calcium hydride is another example. Calcium is always 2+ because it is a second column or group 2 metal. And then each hydrogen would be +1 in this, -1 in this example. But most of the time, hydrogen is not bonded to a metal. It's bonded to a non-metal. And therefore, hydrogen is almost always has a +1 oxidation state. Now, any element that is in elemental form has an oxidation state of 0. And we'll talk about elemental form a little bit more later on. In any ionic compound, another rule I guess you could say is that in any ionic compound, the cation and the anion will match their charges. So for example, if you have calcium sulfide, calcium is the cation and it has a +2 charge, and sulfur is an anion and it has a -2 charge. Those also then match their oxidation states. Or for example, lead chloride. In this one, neither chlorine nor lead are involved in the rules, but you can figure them out because this is an ionic compound. Lead is the positive cation, chlorine is the negative anion, so their oxidation states would match their charges, with lead being +2 and each individual chlorine is -1. the total for any molecule, all of the oxidation states must sum to zero, assuming the molecule has a neutral charge. Of course, the polyatomic ions are not neutral, they have a charge, and so the sum of their oxidation states should equal their charge. So let's do an example here, like nitrate. Nitrate is NO3 and it has a 1- charge. Each oxygen is -2, so I put the oxidation state on top. The total from oxygen is -6 because there are 3 oxygens. The total between nitrogen and all 3 oxygens should equal -1 because the charge on nitrate is -1. Therefore, the total oxidation state, or OS, I guess, is -1. Nitrogen then better be +5. All right, let's do more examples. Oxygen, the rule for oxygen is -2. And the rule for each hydrogen is +1. The total from hydrogen is +2, but when a problem is asking for the oxidation state of hydrogen, we are looking for the individual hydrogen. What is the oxidation state for each one, not the total from all of the hydrogens in the molecule. The oxidation state over here for hydrogen is +1 because hydrogen is making a compound with a non-metal, carbon. The total from hydrogen is +4, so therefore the total from carbon better be -4. And since there's only one carbon, the oxidation state for carbon is -4. The numbers that I put on top of the molecule is the answer to the problem when it's asking what is the oxidation state of each element. The numbers that I put on the bottom, like underneath the molecule, that is the total from all of the atoms of that type in the molecule. So oxygen is -2 individually. The total from oxygen is -10. And because this is a neutral molecule, the total between all the nitrogens and all the oxygens better be 0. What number should we place in this box so that all of the oxygens and all of the nitrogens equal 0? Pause and see if you can work this out. The answer is +10 here. And because each nitrogen is going to have the same oxidation state and there are 2 nitrogens, 10 divided by 2 is +5. So the answer to this problem is on the top here. The nitrogen's oxidation state is +5 and oxygen's oxidation state is -2. Over here we have -2 for each individual oxygen. So we have a total of -6 from the oxygens here. All of the elements added up should be a 0 for the oxidation state. We don't have a rule for chlorine, but we can move to hydrogen because we do have a rule for hydrogen. Hydrogen's oxidation state is +1. There's only one hydrogen, so the total for hydrogens is +1. Then use a little bit of algebra here. And what is the oxidation state of chlorine? Well, that better be +5 so that we have a +1, a +5, with a -6, and that equals 0 altogether. There's only one chlorine, so that one chlorine has an oxidation state of 5. See if you can solve this problem, finding the oxidation states for each element. -2 for oxygen and +4 for sulfur. This is because each oxygen is -2 and the total for oxygen is -4. Therefore, the total from sulfur better be +4. Now try this one. Each oxygen is -2. The total from oxygen is -8, and the total for the sulfur and all 4 oxygens need to equal -2 because this is a polyatomic ion, sulfate, with a -2 charge. Therefore, the sulfur better be +6. There's only one sulfur, so that one sulfur is +6. Now try this one. -2 for oxygen. Therefore, the total from oxygen is -8. The total from nitrogen better be +8, and since there are 2 nitrogens, each nitrogen gets a +4. Again, the numbers that I'm putting on top is the answer to the problem question asking what is the oxidation state of each element in this molecule. Nitrogen's oxidation state is +4. We don't care that the total is +8. We only care about that in order to find out each individual one. We have a -2 and a +1. Those are the rules. Then chlorine better be +1 to make sure that overall oxidation state is 0 for this molecule. All right, now that we know how to assign oxidation states for an element in a molecule, let's go ahead and look at the elemental form a little bit more. So an atom or a substance that is in elemental form has an oxidation state of 0. Any of our metals, here's some metals, certainly not in an exhaustive list, but any of the metals exist as one atom by themselves. So when you see just one lead or one calcium in a chemical reaction, its oxidation state is 0. This is elemental form. It is metallic. It's not in an ionic compound. It's not dissolved in water. It's not in a molecule. It's just by itself. This is what a solid hunk of lead would look like on the molecular symbol. It's just lead, Pb. So all of these oxidation states would be 0. If they were in a chemical reaction, you would put a little 0 right above it, and that is the oxidation state. The diatomic elements, here's the 7 diatomic elements that we have. They are 0. Each individual bromine is 0, and so therefore the total is 0. So you would just, again, write a 0 on top of these. These 7 elements exist as diatomic when they are in elemental form, and they still have an oxidation state of 0. All right, so in an oxidation-reduction reaction, the oxidation states of 2 of the elements are going to change between the reactant side and the product side. So this is the whole point of assigning oxidation states, to determine which one changes from the before to after the reaction. So again, like I said before, one of the elements is going to lose electrons and specifically transfer them to another element. The one that loses electrons is oxidation. Oil rig, oxidation is loss of electrons. Rig is that reduction is gain of electrons, or Leo is loss of electrons as oxidation, and Leo the lion goes grr is the whole phrase. Gain of electrons is reduction. So which of the following are redox reactions? We need to assign oxidation states to every element in this chemical reaction. So we have a +1, total from hydrogen is +4 then, so the total from carbon is -4. Oxygen here is in elemental form, so it has an oxidation state of 0. Oxygen here is -2 with carbon being a +4, and that's because the total from oxygen is, -4, therefore the total from carbon is +4. We don't care about the totals, we're only looking at the changes in the individual atom. -2 and +1. All right, so we can look at carbon. Carbon is changing from -4, right here, all the way to +4. And then hydrogen, right here is +1, but it's still +1 over here, so hydrogen did not change. Oxygen is starting out as 0 and in elemental form on the reactant side, but -2 on both of the other compounds on the product side. So oxygen is 0 to -2. Now, let's compare these oxidation states. Imagine you have a number line. It's a vertical number line here, where the numbers on top of the 0 are positive. The numbers underneath the 0 are negative. We can see carbon is starting at -4 and increasing to +4. So this is oxidation. The oxidation states increased because it lost negative electrons. Hydrogen did not change, but oxygen went from 0 to -2. This is reduction because it gained negative electrons, and therefore its oxidation state is going to decrease. So the reduction is going to decrease on this oxidation number line, but the oxidized element is going to increase on this oxidation line. So the answer then is that carbon was oxidized and oxygen was reduced. And you don't need to say anything about the hydrogen. All right, you try these next 2 problems here. All right, so the middle one here, this double replacement reaction, it is not a redox reaction. All of the oxidation states did not change from the reactant side to the product side. We have a +1, -1, +2, and then nitrogen is a +5, oxygen is -2. Lead is a +2, chlorine is a -1, sodium is a +1, oxygen a -2, therefore nitrogen is a +5. So you can see that nothing changed. Sodium is +1 on both sides, chlorine is -1 on both sides, and so forth. So double replacement reactions are not redox reactions because charges and oxidation states don't change from reactant to product side. There was no electron transfer. This last one, though, is oxidation reduction reaction. Magnesium changed from 0 to +2. Magnesium changing from 0 to +2 is oxidation because that is increasing on the number line. And then hydrogen went from +1 to 0. +1 to 0. That is reduction. It is decreasing on the oxidation number line. Chlorine is -1 here and -1 here, so it did not change. So this is the answer. Yes, it is an oxidation reduction reaction, and your explanation or justification for why and how this is showing which elements oxidized and which one reduced, and how their oxidation states changed. Determine the following, if the following reaction is a redox reaction or not. Provide evidence of oxidation states either way. Go ahead and see if you can work this out. Hydrogen is a +1. Therefore, carbon is a -3, and that's because the total from hydrogen is +6. And the total from carbon better be -6, and there are 2 of them, so each carbon is -3. We don't care about the totals, we only care about the individual oxidation states of each element and how it changes. Oxygen is in elemental form over here, so it's 0. Over here, carbon is -2, or sorry, oxygen is -2, because there are 2 of them. Carbon must have changed, or is +4. We have -2 and +1. So we have carbon changing from -3 to +4. Hydrogen is not changing, +1 to +1. Oxygen is changing from 0 to -2. So carbon increased on the number line, and therefore it was oxidized. Oxygen decreased on the number line, therefore it was reduced.